One of the easiest things to get confused about in chemistry is the difference between mass number and atomic mass. So this lesson is about how are the atomic masses, which are the masses on the periodic table, actually calculated. Mass number was something that we learned in the last lesson about isotopes and individual atoms. So, for example, when we're looking at a particular atom, so like this carbon atom, protons and neutrons, we created a system of weighing their mass using what we call atomic mass units because it's easier than trying to use grams because they're so small. So protons and neutrons are basically the same size. They both weigh what we call one atomic mass unit. And then electrons are so small that their atomic mass actually just rounds down to 0. So they basically have almost no influence on the mass of an atom at all. So what we learned in the last unit was how to look at data on how many protons and neutrons and electrons there are in an atom and put together a symbol that represents that particular type of element or atom of the element. So for example, this one, we would of course start with the C because it's carbon, and then we always include the important number 6 because there are 6 protons in the nucleus of every carbon. In this isotope, we have 6 protons and 6 neutrons, so we have a mass of 12. And we have 6 electrons. So if you have 6 negatives and you have 6 positives, that means you have no charge, so there's nothing there. Okay, but what we learned is there are other types of atoms of the same element. So the number of protons has to stay consistent. But let's say we added another neutron to this nucleus. So just throw in another neutron right there. That means that this number would change to 13. Okay, and there is actually another isotope that we know of called carbon-14 where we have yet another neutron, so then this would change to 14. Okay, so the issue is, why is the atomic mass a decimal point then? Obviously we understand the concept of averages, but if you're looking at the average of going back to these, you have 12, 13, and 14, the average would be 13. Okay, but that's only if you assume that carbon-12, carbon-13, and carbon-14 all occur at equal rates. So like if you have 10 12s and 10 13s and 10 14s, the average would be 13. But that's not the case. Okay, the reason why we have decimals on the periodic table is because some isotopes are more common than others. So if we look at carbon, for example, okay, the term for this is relative abundance. It's the percent existence of a certain isotope. So you can see from this little data set right here that obviously carbon-12 is the high majority of all of the carbon atoms in the universe. 98.89% of carbon is going to weigh 12 atomic mass units. And then a small percentage of them are going to weigh 1.1. The carbon-14 is so rare that we don't even have a percentage for it. And it's radioactive, so it just decomposes over time anyway. So essentially that means that we're not going to be including it in any calculations to figure out average. Okay, the relative abundance of the stable isotopes are always the ones that we use to calculate the average mass. The equation for atomic mass is pretty simple. Okay, if you want to know the average, then you take the mass of the isotope and you multiply it by its relative abundance, and this is going to be in decimal form. Okay, we don't want to use, like 90.89% because that would make all of our atomic masses way too big. So we're going to take the AMU mass numbers and the decimal version of the relative abundance, and you just add all of the isotopes together. So if we start with a really easy one, we can look at boron. It's a great example. The bad news of these questions is they're word problems and it takes a minute to set them up, but you will always know if you have the right answer, because if you're solving for atomic mass, then all you have to do in the end is double check your work by looking at the periodic table and you should have the same answer. So if we know that boron has 2 isotopes and you know that boron 10 is 19.9% abundant and boron 11 is 80% abundant, then we know the average mass is going to be closer to 11. Okay, so these are the rounded numbers, but we always want to use the specific number because we'll get better data that way. So we're going to have a number that's 80% closer to 11 than it is to 10. So if we set this problem up correctly, we're going to take the isotope masses and plug those in. And then we're going to take the relative abundance as a decimal form and plug those in. So you'll get a mass for this one reduced by its percent abundance, and then you'll get a mass for this one reduced by its percent abundance, and you add them together. And what you should get is 10.81 AMU. So then to verify that we did this correctly, you just look at the periodic table, and the average mass of boron is indeed 10.81. So obviously, if you're able to check your answers and know that they're right, the setting the problem up is going to be what someone is looking for if they're trying to test you on whether or not you understand it. Being able to set up the math and then prove why the atomic mass is 10.8 is the whole point of these questions. Like, anybody can look at the periodic table and read a number. So we want to make sure that you're comfortable setting these problems up. Okay, this one's just a little bit harder because it doesn't immediately give you the final answer. We just have a data set of mass numbers and abundances, and even though you can look at these mass numbers and make a reasonable guess about what element this is, you don't know for sure. So we really do need to set up our our math here and solve the problem, because when we get our answer, we should find an exact match on the periodic table. So if we plug in our masses and our relative abundances, okay, we can make a little bit of a prediction here that since this one is 80%, our final answer is probably going to be closest to this number. And if you plug everything in correctly, you should get 24.305 atomic mass units. On your periodic table, you're going to see that this number is rounded to 2 decimal places just because there's not as much room. So 24.31. Okay, that means you should find an exact match because we have the real atomic mass, and the only one that exactly matches is magnesium, which is correct. The rest of these examples are just showing you various different ways that you can be given the information, but it's still really all the same process. So if we're looking at copper, copper also has 2 naturally occurring isotopes, 65 and 63. And it tells you the atomic mass of both of them. 63 is 62.92, 65 is 64.9, but it only tells you one of the percent abundances. So at first it seems like, oh no, I don't have enough information, but really you do. Okay, if there's only 2 naturally occurring isotopes and one of the pieces of information that's missing is a percent, well, you know that 2% should add up to be 100. So if we're looking for the relative abundance of copper 65, okay, you would do 100 minus 69.15. which means that your missing percent is 30.85. So now you have everything you need to set up the problem and solve it just like we've been doing. If we plug in the masses where we know they go in the equation and the relative abundances, then we get an answer of 63.54604, which on your periodic table says 63.55, so that is a match. If we're really trying to throw you a curveball here, you might see an example like this, where it seems like you don't have the right information to figure out the problem, but you really do. So if you have a 400 atom sample of lithium, and 30 of them are lithium-6, and 307 of them are lithium-7, and we're assuming that this 400 atom sample is representative of all lithium, then even though it doesn't directly give you percentages, it does give you the information you need to find percent. So if we wanted to know the relative abundance of lithium-6, you could just do 30 divided by 400, and that would tell you that the relative abundance is 0.075, which is 7.5%. Since we know that we're just going to end up using a decimal later anyway, I'm just going to leave it this way rather than turn it into a percent again. And then lithium-7 is going to be 370 divided by 400, and that is 92.5%. Then once you have the information you need, you can go ahead and just set it up and solve it like we've been doing. So to verify, the 2 mass numbers times their relative abundance do equal what the periodic table suggests, which is 6.941. Of all of the examples that we've looked at, I would say this is probably the only one that will stick out as being different. So it starts off pretty much the same. We have 2 naturally occurring isotopes of chlorine. Chlorine 35, you have the atomic mass and you have the relative abundance. But then all of a sudden everything changes. So it's asking you to use the known atomic mass. So for all of the ones that we've done before, we were solving for the answer. What is the average atomic mass? Now the question is suggesting use the average atomic mass of 35.45 to determine the unknown mass number of the specific isotope, chlorine 37. So the setup process is going to be different. The other piece of information that's missing is we only have one of the percentages. So just like in the question before, the first thing that we're going to do is solve for the easy unknown. So if we know that chlorine 35 is 75 and 0.55%, then we know chlorine 37 is going to be 100 minus 75.55. So it's going to be 24.55, and we'll use that number later. What we don't know is the mass of chlorine 37. We do, however, know that it should be really close to 37. Okay, so all of these mass numbers are just specific values of what we always usually refer to as a whole number. So even though you don't know what it is off the top of your head and you can't look at the periodic table to figure it out, you'll still know if you get the answer right, because you know your goal is to get something really close to 37. So here's how this looks. Instead of using atomic mass on the left side of the equal sign, we're actually going to plug in the atomic mass. And then we're going to plug in the mass of the isotope we know, and we're going to plug in the relative abundance that we know. Okay, the other piece of information is the mass number and relative abundance of the other isotope. Well, we just figured out that if this one is 75.5%, then this one must be 0.2445%. Okay, but what we cannot figure out without doing math is this isotope mass. So really what we're doing is solving for X on the right side of the arrow instead of on the left side of the arrow. For simplicity's sake, I am going to walk you through this step algebraically, because for some of you it might have been a while since we've had to do order of operations. If we have two numbers that are in parentheses, we're going to look at those first. So simplifying the parentheses, we get 26.412, and then we still have the x and 0.2445 in their own parentheses. Our next step in simplification would then be to subtract both sides by 26.419 so that we can get the x and the 0.2445 by themselves. So we end up with 9.03 AMUs equals x times 0.2445. And then now we only have one step left. If we want to get x by itself, we divide both sides by 0.2445. And that gives us our final answer. So the mass of chlorine 37, oops, hang on, let me get that. Chlorine 37 is 36.94 atomic mass units.